All right, grade 11 chemistry. It is our last video. This is it. We're talking about the ideal gas law today. We're going to do some practice problems. A lot of this is just going to be practice problems. So if you watch a few and you feel like you got it down, feel free to finish. But first, I'm going to talk about two things that are near and dear to my heart, which is number one, how a helium balloon works, and number two, how a hot air balloon works. So the helium balloon is easier to explain. The hot air balloon is harder to explain, but both of them are going to be using our ideal gas law. And the ideal gas law has this equation, PV equals nRT. PV equals nRT. P is pressure. V is volume. N is the number of moles and T is the temperature. Now R, this guy here, R is the molar gas constant. It's constant. It has a known number, and you can see that at the top of the page here. That's going to stay up there the entire time to keep in mind. So if we use kilopascals for pressure, liters for volume, moles for moles, and Kelvin for temperature, the value of R is 8.314. So 8.314 kilopascal liters per mole K. It's a heck of a unit. If we use atmospheres for pressure, still volume in liters, still N in moles, and still temperature in Kelvin, if we use atmosphere instead, we have 0.082 atmospheres liters per mole K. And that's going to be true for any gas, or at least we're going to assume that it's true for any gas. It does actually vary depending on the gas, but it's a very tiny shift, like, within a percent. So at this stage in the game, we're not going to talk about it. So this lets us link pressure, volume, number of moles, and temperature. And note that it doesn't matter which gas. We don't care which gas. Molar mass doesn't enter into it. What kind of gas doesn't enter into it? Every gas can use this equation. So why is this so cool? Well, we can explain this using an example, and this is the how do helium balloons work. You guys know, you blow up a balloon with helium, it floats, it goes up. Well, what's going on there? Well, imagine two balloons. Let's say they're both 2-liter volume. Let's say they're both at 20 degrees Celsius. Right? And let's say it's just normal atmospheric pressure. The pressure inside and outside the balloon, inside and outside, is going to be equal because it's a balloon, 101.3 kPa. I realize that the rubber is going to add a little bit of pressure to the inside, but let's just pretend that that doesn't happen. Inside and outside. Let's say it's 101.3 kPa of pressure. Right? They're both the same balloons. They have the same liters, pressures, and temperatures. One thing about temperature, though, remember we have to be in Kelvin. So let's just turn this to Kelvin right away. 20 Celsius is 293 Kelvin. I'm just adding plus 273 to that, 293 Kelvin. So they have the same parameters, which means if we use our equation, I'm going to bring this over a little bit, our equation is PV equals nRT. PV equals nRT. We know P, it's 101.3 kPa, that's P. We know V, the volume, is 2 liters. I just arbitrarily chose 2 liters. We know R, that's up there. You can see it, 8.314. And we know T. It's 293 Kelvin. which means we can solve for n, for the number of moles. Right, n is equal to, when we want to rearrange this thing, we can rearrange it for n. We're going to divide by RT on both sides. Right, divide by RT to get RT out of here, because if we divide by RT, those reduce to 1. So we're going to end up with n equals PV over RT. And then all we have to do is put in the numbers we know. N equals pressure, 101.3 kPa. That's pressure. Volume, 2 liters. Over, divided by R. We need our unit for R. We need to know what we're using R in. Well, we got kPa and liters and K, Kelvin. So if we look up here, we see it's 8.314 kilopascal liters per mole K. So 8.314, technically kPa liter per mole K. 8.314. And then the last thing is the temperature here, T. For temperature, 293 Kelvin. We have to be in Kelvin down here, or else it's not going to work. 293 Kelvin, because we want to cancel that Kelvin down here with the Kelvin up here. We'll cancel the kPa with the kPa, the liters with the liters, we'll be left with just moles. I'm going to put that through my calculator. Handy dandy calculator. 101.3 times 2 divided by, if you're going to do it that way, make sure that you're opening brackets when you divide by 8.314 times 293, or you can just do the divisions into 2 steps. And what I get here when I do this, n is equal to 0.083 moles of gas. Moles of gas. That's how many moles of gas are in my balloons. Right? Either one, both balloons. It doesn't matter what gas is in there. PV equals nRT doesn't care what gas it is. We just know that there are that many moles. We can calculate the number of moles. Now, let's pretend there's different gases in there. Remember, this section is called How a Helium Balloon Works. How does a helium balloon work? Well, if this was helium, say, and this was air, let's just pretend it's nitrogen. As you guys know, air is mostly nitrogen, so we can assume that it's going to be pretty close to nitrogen. We could work out how much it weighs now. We work out how much it weighs. Helium is 4 grams per mole. Nitrogen is 28 grams per mole, or close enough to it, right? 28.14 or something like that. 0.14. And they both have equal moles of gas, equal numbers of moles. So if we want to figure out how much these balloons weigh, I have my 0.083 moles down here. This one's 4 grams per mole. To get the mass, it's just going to be 4 grams times 4 grams per mole, I should say, times 0.083 moles. 4 grams, 0.083 moles. We'll get a mass. 4 times 0.083, 0.332 grams of helium in that balloon. 0.332. 332. Now on this side, I have 28 grams per mole, so 0.083 moles times 28 grams per mole is going to give me 2.3 grams. Right, 2.3 grams of nitrogen versus 0.3 grams of helium. So we can see here why the helium balloon will float. It literally has less mass because the pressure of a gas, because the volume of a gas does not depend on what gas is in there, but the mass of it does. And this is what the ideal gas law and all these other gas laws help us understand. So the helium is literally lighter than air, because air will be approximately this weight. That equal amount of air will be approximately that weight. So it'll float, it'll go up, because it's lighter than air. So it's just very interesting. That's how helium balloons work. Next up, we're going to explain how a hot air balloon works. So let's, how hot air balloons work. I probably misspelled balloons there. All right, how hot air balloons work. This is a little bit trickier. But we can still use PV equals nRT. Let's diagram a hot air balloon. You guys have seen hot air balloons before, I'm sure. There's an open hole at the bottom and a big canopy, very, very big canopy, but the hole is open. And underneath there hangs the little basket, right, the little basket that hangs there. I'll draw a little basket. Terrible basket. There we go. The basket that hangs there, and there's a burner attached as well, right? So there's a little burner, right? A little burner on the basket. But the important thing there is that it's open. It's open to the environment. Gas can come in and out, right? Gas can easily come in and out. And because it's open to the environment, that means that the pressure on the inside is equal to the pressure on the outside. So the pressure on the inside is equal to the pressure on the outside. And the volume of the balloon is fixed, right? The volume of the balloon stays put as well, because once it's inflated fully, it's fully inflated. It's not going to get any bigger than that. So what happens here is that the temperature, right? What actually happens here between cold and hot. I'll do another diagram of a hot air balloon. Right? If it's cold, it's low temperature. If it's hot, it's high temperature. Hot is high temperature, cold is low temperature. And so we can use our concepts, our molar gas law, to have a look at what happens. The pressure is the same, both balloons. It's just air pressure. The volume is the same, both balloons, because it's kind of like a rigid balloon. But this one's low temperature, this one's high temperature. In PV equals nRT, we know that this one follows this law, PV equals nRT, and this one also follows this law, PV equals nRT. Right? They both follow the same law. So we can kind of organize it. The P stays the same and the V stays the same, right? This number is the same on both. And R is the same on both too. Which tells us that we can make a new law. N1T1 equals N2T2 because we can set these equal to each other and cancel out the R. That tells us that if the temperature goes up, the number of moles must go down in order to keep the same number as the other side, right? You were increasing one, we have to decrease the other. So yeah, basically the higher temperature, because we're keeping the same fixed pressure, forces more moles of gas out. Because there's less moles equals less mass equals, float. Right? It means you go up. So yeah, technically hot air balloons don't have to be, flexible. They can be rigid, and you'll get exactly the same concept happening. So that's how a hot air balloon works. Let's try some practice problems with the ideal gas law. Practice problem 1. Oh, that said how hot 8 balloons work. That's fine. Practice problem 1. Here's practice problem 1. Okay. Practice problem 1 for the ideal gas law. We're actually doing number 2 here. So it's number 2 on this worksheet. We've got a sample of 1 mole of oxygen. It doesn't matter what the gas is. It doesn't matter. At 1 mole of oxygen, 50 degrees Celsius, 98.6 kPa. So let's write that out. 1 mole, that's N. N is 1 mole. 50 degrees Celsius, that's a temperature. That's 50 degrees Celsius. But remember, we want our temperature in Kelvin. Let's just throw that straight to Kelvin. 50 degrees plus 273 is going to be 323 Kelvin. I think that's right. I'll just double check that. 50 plus 273. Yeah, 323 Kelvin. Then we got volume is 25 liters. So V, 25 liters. 25 liters. The question is, oh, it's not 25 liters. Never mind. It's not V. We don't have V. What am I talking about? I was looking at the next question. That's what was going on. P. Pressure is 98.6 kPa. And they want volume. Volumes are question mark. How much volume is it? Well, we have our equation PV equals nRT. We want to solve for volume, so we divide by P on both sides. Volume is nRT over P. That's our equation. We have to figure out which version of R to use. R, here we have kilopascals as our pressure measurement. So we look up there, 8.314 kilopascals. The rest of it works. We got moles, we got Kelvin. We're going to get an answer in liters. So we're going to use our 8.314. So it's 1 mole times 8.314 kilopascal liter per mole K times our temperature, 323 Kelvin. Gotta remember to be in Kelvin for it. And divided by the pressure, which is 98.6 kPa. And then our answer there is going to be some number, clear, 1 times 8.314 times 323. And we will divide that by 98.6. 27 liters, 27.2 liters. 27.2 is what my calculator gives me, and I need a unit. Well, liters is my unit of volume, because the kPa cancels kPa, moles cancels moles, K cancels K, liters is the only thing left, so liters. That's how we figure out what unit to use. Okay, as that's solving for a volume, we can try a few other ones. Let's just go a little bit further down here. How about this? All right, number 5. Question number 5. A little bit trickier. Let's write out what we know. The pressure in a certain gas line. Let me just change it to practice problem number 2. Practice number 2. Practice problem number 2. When the pressure in a certain gas cylinder with a volume of 4.5 liters. Oh, hey, we have a number. Volume of 4.5 liters. V equals 4.50 liters. That's a volume. Reaches 500 atmospheres. The cylinder is likely to explode. So let's write that. Explodes at 500 atmospheres. If this cylinder contains 40 moles, moles is N is 40 moles, and T is 25 degrees Celsius, which, oh hey, it's temperature. Temperature has to be in Kelvin. We got to be in Kelvin. So it's 298 Kelvin. Is it on the verge of exploding? So the last thing that we can solve for here is pressure. Pressure is our question mark. Same concept. We can write out PV equals nRT. PV equals nRT. We're solving for pressure. Right, we're solving for pressure. So that's dividing by volume on both sides. Volume will drop out. It'll try to reduce to 1. P equals nRT over V. nRT over V. So let's put those in. N is 40.0 moles. R. What are we using for R? Right? We have two versions of R up there. We have 8.314, which is in kilopascals. We have 0.082, which is in atmospheres. Well, if we look at what we know, this thing explodes at 500 atmospheres. So we might as well get an answer in atmospheres. Why not? Let's use our atmosphere version. 0.082 atmosphere per mole K. The temperature, 298 Kelvin. Temperature is 298 Kelvin. It's kind of looking a little weird there. Divided by the volume, 4.5 liters. When I put it through like that, we can figure out this thing 40 times 0.082 times 298. Divide that by 4.5, 217. I get 217. So P is equal to 217. What's our unit? Moles will cancel moles. Kelvin cancels Kelvin. Liters cancels liters. Atmospheres. We chose the atmosphere version for a reason. So atmospheres. So it's currently at 217 atmospheres. It bursts at 500, so it's not even halfway there. I think we're okay. And we calculated our pressure in atmospheres. Okay, we're going to go to practice problem number 3. It's the last practice problem. And then I'll finish the video there. That'll be the end. What we're going to do is we're going to calculate the molar mass of a gas. Let's find one. Okay, yeah, this one works. The density of a certain gas. Actually, no, we'll do 2 more practice problems. First one. First one's going to be number 10 here, actually. What volume is occupied by 0.25 grams of oxygen measured at 25 degrees Celsius and 100.66 kPa? So let's run down what we know. We know that PV equals nRT. nRT. PV equals nRT. What do we know here? Number 10 here. We know that T is 25 degrees Celsius, but we have to be in Kelvin. 298 Kelvin. T is 298 Kelvin. What else do we know? 100.6 kPa. 100.6 kPa. That's P. 100.66 kPa. We want V. V is our question mark. We know R. R is a constant. It's in kPa, so we'll use 8.314 for R because that's the kPa version of R. What we don't know is N. Right? If we knew N, we'd be able to solve it. We'd be able to get V, because once we know 3, we can get the 4th. But N, we are given that it's 0.25 grams of oxygen gas. 0.25 grams of O2. So what we do is we pull out a periodic table. We're going to need a periodic table here. And we find oxygen. Oxygen is 16 grams per mole. There it is. But there's O2. So O2 is 32 grams per mole. We can work out how many moles we have. Right? 0.25 grams times what goes on top, what goes on bottom. Well, grams goes on the bottom, moles goes on the top. 1 mole per 32 grams. Is equal to, is going to be a very small number of moles. 0.25 divided by 32. Very small, 0.0078 moles, right? Moles, because grams cancels grams. Moles of O2. Hey, now we have N. We have that. We just solved for N. Hey, back to unit 3 type stuff. 0.078 moles. And now we can solve for V. Solve for V. PV equals nRT. Divide by pressure so that we can isolate volume. Volume is nRT over P. nRT over P. So that's going to be N times R times T over. So 0.078 moles times. We've got our pressure in kPa. Our pressure is in kPa. So we are going to, so I'm just going to circle this a little bit more. Our pressure is in kPa, so R is going to be 8.314 kPa liter or mole K. Don't worry if you can't see the unit there, it's fine. And the temperature, 298 Kelvin. We're dividing that by 298 Kelvin, 298. This is temperature. Temperature from here, dividing by the pressure, 100.66 kPa. That's why we wanted this in 8.314, because it's the kPa. kPa will cancel out. And our volume then is going to be, well, just whatever that is. So times 8.314 times 298. Now we're going to divide it by 100.66. Easy, 0.19. 0.19. 0.19, what? 0.19, I need a unit. What unit? Well, it's kPa liters. If you look up there, liters. So liters, the answer is going to be in liters, because that's what unit of R we use. Those are the units of R. Hey, we're going to round things out with our last practice problem, which is going to be question number 9 there. Practice problem 4, which is already up on screen. It's question number 9. Erase this. We'll keep PV equals nRT up there. Why not? PV equals nRT. PV equals nRT. PV equals nRT. Now this is interesting. Number 9. The density of a gas. Density is 2.53 grams per liter. Density is 2.53 grams per liter. Density, by the way, it has a symbol. It's rho. It looks like a weird little lowercase p, but it's not quite a lowercase p. So that's 2.53 grams per liter. Right. And what that means is, if you think about it, is I have 2.53 grams of this stuff in 1 liter. 2.53 grams in 1 liter. 2.53 grams in 1 liter. What I'm looking for is grams per mole. Right? I'm looking for grams per mole. I have grams per liter. I want grams per mole. Well, that means I need to figure out how many moles of gas, right? I need to figure out how many moles of gas are in my 1 liter. So how many moles are in 1 liter is going to be the question that we're going to ask ourselves. How many moles of this gas are in 1 liter? Because grams per mole, well, I already have grams. I already have grams. I'm going to use this. I'm going to use PV equals nRT to solve for moles. If PV equals nRT, PV equals nRT, N is what we want to solve for. We want to solve for N. We're going to divide by RT on both sides. So N is PV over RT. And is PV over RT. And we have pressure, volume, and temperature, assuming we say that we have exactly 1 liter. So we can solve it now. Pressure is 98.66 kPa. 98.66 kPa. Volume, we decided it was going to be 1 liter because we just then divide our 2.56 by the number of moles. So if we keep it to that, so 98.66 kPa. We have 1 liter. 1 liter. We divide it by R times the temperature. So R, which R are we using? What's kPa? So we want the kPa version of R. We look up there. It's the 8.314. 14 kPa liter per mole K. Liter per mole K. And then lastly is the temperature. Oh, I didn't do the temperature. So the temperature here is 27 degrees Celsius, which means I have to add 273. Oh, look at that. It's exactly 300 Kelvin. 300 Kelvin. So divide by 300 Kelvin. So the number of moles of my gas, which is what I'm solving for, 98.66 times 1 divided by 8.314 divided again by 300, very small, 0.0396 moles. It's moles because it's N. It's moles because we cancel kPa with kPa, liters with liters, Kelvin with Kelvin, and we just end up with moles at the end of the day. So that's how many moles I have. So that means that I have, if I combine these, right, I have, I'm going to change colors. I have 253 grams. I have 0.093 moles, 0.0396 moles. I'm going to put them together. It's grams per mole. Right, the molar mass, it's 2.53 grams in 0.0396 moles. And we just put that together. 0.396. That's getting really fuzzy for some reason. 396. So 2.53 divided by 0.396. 2.53 divided by that. 63.96 grams per mole. So this is the kind of stuff you can do. You can combine these things and figure out molar masses and things like that. This is actually how molar masses were initially determined, because everything was in gas phase. It was easy to measure temperatures, volumes, and pressures. Much harder to get a count of individual things. But once they got the gas laws in place, they were able to actually do stoichiometry and figure out this kind of stuff. So yeah, that's it. That's the lesson, and that's actually the course. We're done. I hope you enjoyed it. I certainly did. I'll see you guys in class to round it out, and then we're just going to be doing review for the final summative for the rest of the class. Yeah, thanks a lot. It's Mr. B signing out.